So, we are discussing about conjugate gradient method and actually trying to develop a method based on our previous knowledge of full orthogonal methods and direct Lanczos algorithm for tridiagonal method in Krylov subspace method. So, started with a giving an initial background on Krylov subspaces, and then looked into Arnoldi modified Gram-Schmidt and full orthogonal method algorithm, and obtained the relationship between the residual and the basis of residual at mth step and the m plus 1th basis of Krylov subspace, and observe that how it can be obtained for a tridiagonal for a symmetric matrix A, where the Heisenberg matrix H is of tridiagonal form. This is what we have done in the previous lecture. So, we can quickly look into the symmetric linear system solver in Krylov subspace, which we have discussed earlier, direct Lanczos method. The Lanczos method finds an approximate solution of x m is equal to x 0 plus v m y m, which is a Krylov subspace method. This is x m is equal to x 0 plus k m a comma r 0. Let me write it down again. This is same as x m is equal to x 0 plus k of a r 0 k m, and this is a Krylov subspace method. And it uses inversion of tridiagonal matrix T m, where Arnoldi's method will give us H m, and H m is equal to T m for symmetric matrix. H m is T m a tridiagonal matrix, and this comes from the full orthogonal method. So, essentially it shows that this is an orthogonal method, where y m is found out by inverse of the Heisenberg matrix, which is of tridiagonal matrix now. And a TDMA type of algorithm, tridiagonal matrix algorithm, can be used for direct and first inversion of the tridiagonal matrix. And this starts with the step that T m, the tridiagonal matrix, is product of a lower triangular matrix. So, I can write T m is equal to L m into U m, and an upper triangular matrix, and we can substitute it. X m is equal to x 0 plus V m, y m is T m inverse B y. So, this is T m inverse y is y m here, and further one step gives us x m is equal to x 0 plus V m U m inverse L m inverse y. This is what we have done in the Lanczos algorithm earlier. And x m is equal to x 0 plus V m U m inverse L m inverse y. We can now say that this V m U m inverse, this is what we do in a TDMA type of algorithm. We have divided this as U m inverse L m inverse, and write two different forms of the matrices. P m is equal to V m U inverse, and Z m is equal to L m B m inverse. So, we can write x m is equal to x 0 plus P m Z m, and then we find an iterative relation for calculating P m, which is the last column of P m based on, and we will change the values of m recursively and get different columns of the matrix P m. And using this recursive relation, we can calculate what is P m. From there we get V m U m inverse, and similarly Z m is also calculated using a recursive relation. So, this recursive relation is heart of a tridiagonal matrix algorithm. And we have done it in very detail when discussing about direct solvers for tridiagonal matrices, which is tridiagonal matrix algorithm or Thomas algorithm. Remember when we did looked into finite difference approximation of one dimensional heat conduction equation or one dimensional Laplace equation, and got a tridiagonal matrix, and then observed that instead of doing Gauss elimination or TDM using recursive relation, we can write an TDM algorithm which will give us very fast solution. So, this can be utilized here. So, this is how the direct Lanczos method works, that using this recursive relationship you find Zm and Pm, and then you substitute Pm here and Zm here, and then you write Xm is equal to X0 plus Pm Zm. One important vector that we construct in this method is the auxiliary vector Pm. We are using a recursive relationship for finding out Pm, and if we can do it in a more elegant way, we can probably get a very much better solution here. The problem with recursive, there is one very significant problem with recursive relation, that when it in today's date talk about parallel computing etc., recursive relations do not work in parallel computing. So, if this recursive relation can be substituted by some other method, we will probably get a better solution algorithm. So, we focus on looking into the auxiliary vector Pm, and interestingly some further characteristics of auxiliary vector will come out in a while. So, in the direct Lanczos algorithm, Xm is obtained by a recursive relationship as Xm is equal to Xm minus 1 plus Xim Pm, and Pm and Xim are found using recursive relations. Now, with this background, we will probably try to look into more detail on the properties of the auxiliary vector Pm, because till now, till coming into Lanczos algorithm, we are only interested about the residual R and new residual Rm, initial residual R0, and Vm, what are the basis of Krylov subspace, and the Heisenberg matrix Hm and Vm comes out of the Arnoldi modified Gram-Schmidt method, and based on my initial guess, I can find out what is the initial residual R0. If we have R0, Hm and Vm, full orthogonal method tells that we should be able to find out Fm is equal to Xm is equal to X0 plus Vm Ym, right. So, full orthogonal method tells us Xm Fom, full orthogonal method, is equal to X0 plus Vm Ym, where Ym is equal to Hm inverse of basically beta E1, where beta is equal to mod of R0. The problem in the full orthogonal method that we have to find out inverse of a upper triangular matrix, which is not as probably not as costly as a general matrix A, because A can be of any shape and this is an upper triangular matrix. However, this will involve certain number of steps, at least the steps for required for back substitution of a Gauss elimination process. So, instead now for for symmetric A, Hm is equal to Tm, and we get Y is equal to Tm inverse beta E1, which is now the de Lanczos method, which we are discussing here, and this Tm is tridiagonal. So, inverting this Tm needs the recursive relationships and recursive steps, like find out Xim, find out lambda m, find out Pm, all these recursions are related for inverting Tm efficiently. Now, this particular Pm we have introduced for while we are looking into inversion of Tm inverse. Instead of writing that Xm is equal to X0 plus Vm Tm inverse beta E1, I write xm is equal to xm minus 1 plus im pm. So, this is a new vector or an auxiliary vector which we are introducing at this stage. Let us look into the auxiliary vector into little more detail. And there comes a proposition that Rm is equal to b minus a xm for different values of m be the residual vectors produced by Lanczos or de Lanczos algorithm, that is for symmetric A matrices. Right. When we write Lanczos and de Lanczos, we have ensured that for symmetric A matrix. This is important, it is only for symmetric matrix. And Pm, m is at different values of m 0 to 0 1 up to larger numbers. Pm are the auxiliary vectors produced by de Lanczos algorithm. And then each residual vector Rm is such that Rm is equal to sigma m Vm plus 1, where sigma m is certain scalar. As a result, the residual vectors are orthogonal to each other. Exactly this we have discussed in the last session, that Rm gets the form, let me write it down for you, Rm Rm is equal to minus beta m plus 1 e to the power m t ym Vm plus 1, this form. And there is another proposition which is more important, the auxiliary vectors Pi form an A conjugate step, that is A Pi Pj is equal to 0 for I naught is equal to 0. So, A P I, and if we take its dot product with Pj, this is equal to 0 for all I not is equal to j. Or we can write P transpose A P is a diagonal matrix. That is, only when Pi transpose A Pi that row will come, that will give a diagonal 1 value, and for all other combination of I and j it will give us zeros. So, this is called a conjugate step here. This is the let me use a different pen. This is the A conjugacy, that API dot Pj is equal to 0. We will show that it is actually coming to 0, or P transpose AP is a diagonal matrix. So, P's are being utilized for deriving the recursive relation. Now, what we can see, and they are also following a recursive relation, what we can see is that before going instead of going into the recursion, probably if I can have one P, I can get idea about the other P's simply by the fact that each P is orthogonal to the other P multiplied with A. P transpose AP is equal to 0 in case of I is not equal to j, or P transpose AP, the capital P transpose AP matrix, P is the columns of small p and the columns of capital P. P transpose AP is a diagonal matrix. The first proposition follow directly from Arnoldi's method, which we have seen earlier, and Arnoldi's method for I think we should write for symmetric A, where we can write beta, right. And the proposition 2, A conjugate prevectors, we need to show that Pm transpose Apm is a diagonal matrix. Pm is Vm Um inverse, that is how the auxiliary auxiliary vector matrix is defined. Pm transpose Apm is Vm Um inverse transpose Avm. So, AB transpose is B transpose A transpose, that will be UM inverse transpose into VM transpose AVM. Now, from Arnoldi's method, what we have seen is that VM transpose AVM is equal to the Heisenberg matrix HM. And which is same as the tridiagonal matrix Tm for symmetric matrix. So, what we get? Pm transpose APM is equal to UM inverse transpose Tm UM inverse. Tm is a tridiagonal matrix, UM is a upper triangular matrix. So, Tm UM inverse gives us a lower triangular matrix LM. This can be verified very easily by looking into the properties of triangular matrix and their inverses and transposes also. So, PM transpose APM is equal to UM inverse transpose UM inverse, and TM UM inverse is the, because UM is an upper triangular matrix. So, TM UM inverse will be a lower triangular matrix LM. So, PM transpose APM is equal to UM inverse LM. Inverse transpose LM. LM is a lower triangular matrix, UM is a upper triangular matrix. So, UM's transpose inverse multiplied by LM, that also gives us a lower triangular matrix. So, PM transpose APM is a lower triangular matrix. Now, we see that A is a symmetric matrix. So, if we take look into PM transpose APM, this is also a symmetric matrix. A symmetric matrix is of lower triangular form. So, A is symmetric, therefore, PM transpose APM must be a symmetric matrix. PM transpose APM, a symmetric matrix, this is PM transpose APM, which is said to be of a lower triangular form. So, these are zeros here, all the above diagonal terms are 0 here. This is also symmetric. So, the numbers beyond the below the diagonal must also be 0. So, this should have the form of the diagonal 0 and 0. A symmetric matrix is also both upper and lower triangular, upper triangular as well as lower triangular. So, lower triangular matrix can only be symmetric, same for an upper triangular matrix, it can only be a symmetric when it is a diagonal matrix. Therefore, PM transpose APM must be a diagonal matrix, and we get the fact that P or small p is a conjugate vector, or I will write small p instead of p. All the columns PM are a conjugate vector. So, now how can we utilize this for deriving a new solution algorithm? This is called the conjugate gradient method. The algorithm is one of the best known iterative techniques for solving sparse system positive definite linear symmetric positive definite linear matrices. Symmetric positive definite matrix which are sparse can be solved by this method, and this is one of the best known methods. We will show it in a while. This method minimizes the function f x is equal to half of x transpose x minus x transpose b for symmetric positive definite matrix A. As there is a general projection method, so the idea comes from the steepest descent type of algorithm, that it should minimize a function along a particular direction, and minimization of f x is, we can show it very easily, is the solution of x is equal to b. Similar to D Lanczos algorithm, x is updated as xj plus 1 xj plus apj. So, they have a recursive like relation for xj. No, it is an should not say it recursive relation, rather iterative relation for xj. The difference is that the recursive relation for P will be substituted by the A conjugacy theorem. Therefore, the residual vector will follow A x j. If I multiply A both sides, A x j is equal to A x j plus A alpha p j, substitute both sides from B, B minus A x j plus 1, which is the residual R j plus 1 is equal to B minus A x j, which is the residual R j minus alpha j A p j. Now, we have the earlier first proposition that R j is are orthogonal to each other. So, if I take a dot product of with R j in the both side, R j plus 1 R j transpose will be 0, and we can get using the values of R j and P j. So, if we can get alpha j. So, if I know about the residual and the auxiliary vector at any jth level, I can find out the coefficient alpha, I can find out the coefficient alpha through which x will be modified in that level. So, as R j's are orthogonal, orthogonal means this A b is equal to 0, I think we have probably discussed in somewhere. So, A b is equal to means B transpose A. So, R j plus 1 R j is equal to 0 means the dot product or dot product of R j and R j transpose R j plus 1 and R j 0. R j plus 1 is R j minus alpha A p j. If we substitute, we get a relationship for A. A is equal to R j dot R j divided by R j dot A p j. The first basis vector P 1 is a gradient, and this is the main idea of conjugate gradient. Choose the first basis vector P 1 is the gradient of f at x 0. The first basis of P, auxiliary vector space P, is the gradient of gradient f at x 0, which equals to x 0 minus b. This is the first basis vector. The other vectors in basis will be conjugate to the gradient of f. Each next p k plus 1 is defined to be a linear combination of r k plus 1 and p k under this conjugacy constant. The direction of p k plus 1 is given by the projection of r k plus 1 onto the space orthogonal to p k with respect to the inner product induced by A. Seems little complicated way of how the mathematical formulations are put into statement, but if we look into the step that the direction for p k plus 1 is the each next p k plus 1, the first p 1 is same as x 0 minus b as the residual. The next auxiliary vector is the combination of the new residual vector and the old auxiliary vector. This is how we are constructing it, fine. So, A p j dot R j is equal to A p j dot p j, that means I can write R j, here we can write R j is equal to p j minus beta j minus 1 p j minus 1, and I substitute it here. That is that what is the conjugacy, what is R j transpose A p j? This is A p j into p j beta p j minus 1. So, this is A p j into transpose p j minus beta j minus 1 A p j p j minus 1, and this is equal to 0 from the conjugacy constant we have already found out. So, started with the fact that next each auxiliary vector is the previous is a linear combination of previous auxiliary vector and the present residue vector, and then we take the dot product of one auxiliary vector with the residual vector at A conjugate dot product, and it comes out to be A p j p j. and substituting. So, beta j minus 1 becomes 0, right. And now, if we take a APJ Rj is found out, if we take a dot product of, I think I have missed one step here. So, you can probably go right like this. So, now from this how to find out beta, what should be the linear combination of P that should be added with Rj plus 1. So, I can start working like this, that Pj plus 1 is equal to Rj plus 1 plus beta Pj, beta j Pj, and then Pj plus 1, and then take the dot product of the entire thing with Apj, take a dot product with Apj of the entire thing, and this will be 0. So, this is Apj Rj plus 1 plus beta j Apj Rj, and Pj Rj we have found out Apj Apj. So, using this, so like I can write this transpose this, if I do take this dot product. From there I can find out what is beta. Beta is minus Rj plus 1 Apj by Pj Apj, alpha j is equal to Rj Apj Rj. And this particular derivation I will not do it right now here, but this is exactly same as the derivation of alpha j, which will follow from here. Take a dot product of this expression with Apj, and you will find out, you will arrive in this particular expression of beta j. So, what beta j needs is Rj plus 1 Apj divided by Pj Apj. Now, for this is a matrix vector product multiplied with a vector. Matrix vector products are computationally expensive, though we are doing it once here. Now, this can be very changed by substituting Rj plus 1 is equal to Rj minus alpha j Apj, and if we substitute this Rj plus 1, here, we get beta j is equal to Rj plus 1 by Rj. So, if we start with one value of Rj transpose Rj, and at next stage we again evaluate Rj transpose Rj, the ratio will give us the beta j. So, this should be sufficient to update P as well as to update X and R. R also can be updated using alpha, X is updated, right, X is always updated like Xj is equal to Xj plus 1 is equal to Xj plus alpha j Rj. So, with these updates we can now finish the conjugate gradient algorithm, and we will look into it in the next session. Thank you.